when you are going to have intersection, there is going to be relative motion, right? There is going to be a relative motion. So at that point, adding a source term is just unbelievably tricky and most likely going to be wrong. So the only way you can actually set up or run these type of simulations is by using a transient solver. And that is a huge problem. In fact, 1 or 2 years back, there were only 2 companies that were actually able to do these type of problems. And any company that does, for example, ANSYS would claim ANSYS or CFX, all the primary turbomachinery simulation providers would claim that they can run these type of simulations. But if you look at their papers, they would all be using a mesh from a particular university in London, which I think that particular university has developed a product called as SCORG, which is basically a mesh generator program. They used a very complex meshing algorithm to, they create the entire mesh for a supercharger, and then all the companies like ANSYS, Star CCM, they pretty much use this mesh, and they use their flow solver, right? Now, Converge can do these type of problems very easily. And for those of you who do not know Converge, whenever the geometry is very, very complex, and whenever you are moving geometry, Converge is one of the best solvers that you can use. What about ANSYS in comparison with Converge in case of compressors? Well, if the models are transient, right? See, compressors are inherently transient. If you take centrifugal compressors, the ones that you have for compressing air in shops, right? They have something called as reed petals. So these are valves that basically open based upon pressure difference. Now, if you actually have to do a CFD analysis on it, you actually have to simulate those things as well. And for that, ANSYS is extremely tough to use. And how do I know this? Well, before starting up Skill-Lync, I was actually working at Converge, and for the last 5 to 6 years, I used to work with companies like GM, Ford, and Hyundai, where we would basically work on internal and external flow problems, and that involves a lot of benchmarking. For the same case, we would use multiple CFD tools, and whatever I'm claiming is based on that observation. So now let's take a look at an animation of the same thing. So here we are going to be looking at, say, a few different screw compressor designs. So let me just pause it here, and let me just point you to some very interesting features in the simulation. So here, this is your adaptive mesh refinement. Look at the structure of that, right? If you're creating computational mesh on your own, there is no way that you'll be able to refine the mesh like that. There's absolutely no way that you can guess that the mesh is going to be there. So again, here we are looking at different types of compressor blades. So like I said, this is the male and female type, and this is just a same thing. So on the top, I believe we are showing temperature, and in the bottom, I believe we are showing pressure. So why do people run these type of simulations? Like I said, they do it to calculate the pressure differences. Actually, I think this might all be, yeah, the top is velocity for sure, and bottom is, and one of them is pressure. So people run these type of simulations primarily for understanding how flow behaves through their entire system. And then they will take the data from this type of a system for a further analysis. All right. So for example, the pressure boundaries, the pressure that you get from this type of from this type of an analysis can be used for NVH simulation, basically for noise analysis, noise and vibration analysis, right? So if you have to get that correctly, in order for you to get any downstream simulation to be simulation correctly, you need the upstream results to be right. Meaning, if your supercharger simulation data is wrong, then any analysis that you do with that data is also going to be wrong. I hope that makes sense.